Okay, so I was going to do a couple of quick shear moment diagrams by uh, graphing where we don't have to write the equations. So remember, step number one is always find reactions. Okay, so we'll need a free body diagram to do that. And let me take this out so we don't have those lines underneath. Okay, so I'm going to draw a free body diagram. I recognize that I have a pin at A and a roller at F. So when I draw that free body diagram, let's come down here. Okay, I have a pin at A and a roller at F. You know, we'll just do it all the way across, just like what we can see our beam is. So at A, I have AY, and I have AX, and at F, I have FY. All of that on there. Not really. Okay. I have a moment applied here at B. So at B, I'm going to put that moment on there, and it's 120 kilonewton meters. At C, I have a 45 kilonewton point load, 45 kilonewton. Okay. And then from D to E, I have a rectangular load. And remember, we're just integrating. We're finding that area into the curve. So area is base times height. So I have 3 meters times 30 kilonewton per meter, which gives me 90 kilonewtons. And I need to remember for a rectangular section that the centroid occurs right in the middle. Okay, so if we come down, we can see that that's going to be 1.5 meters and 1.5 meters. Okay, so we are going to come down here and we have 90 kilonewtons. And then over here we have that roller. So let's look at distances then. And I don't know why this is not, there we go. Okay, so we have 2 meters. We have 2 meters. We have 2 meters. 1.5 meters, 1.5 meters, and then we have 3 meters. So the first thing I'm going to do is sum forces in the x direction. So I have my rule, summing forces, x direction to the right is positive. I have ax, nothing else in the x direction, equals 0. So we're going to box that in. Now we're going to sum moments about, doesn't matter, let's sum them about A. So my rule is I'm summing moments. I'm summing them specifically about point A. I'm using right-hand rule. They equal 0. So I'm going to cover up A, and I've got 120 kilonewton meters. Okay, that's an applied positive moment. I have minus 45 kilonewtons times 1, 2, 3, 4 meters minus 90 kilonewtons times 1, 2, 3, 4, 5, 6, 7.5. 7.5 meters, okay, plus Fy times 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. 12 meters. And all of this equals 0. Remember, everything, my rules are on the left. Okay, what I'm doing is on the left, it equals 0. And so I'm going to get out my handy dandy calculator, and I have 120 enter. And then I have a negative 45 4 times. I have a negative 90, 7.5 times. And I'm going to add, take it to the other side, and then I'm going to divide by 12. And I get that Fy is 61.25 units, kilonewtons, direction up. I got a positive, so it's in the direction that I assumed it was. So now we're going to sum forces in the y direction, up being positive. That's our rule. And again, we are in static, so everything equals 0. So if AY minus 45 minus 90 plus 61.25 equals 0. So I can solve then that AY, so we have 45, change signs, we have negative 90. We have 61.25 positives plus plus. We're going to take those over to the 0 side, and I get 73.75. Okay, so I would box that, show my arrow, and there we go. Okay, so I'm going to come back to my picture, and I have 73.75, and over here I have 61.25. Okay, so now we're going to start. We need to draw a line so that we know we're working with our shear, and we have our 0 shear units. Make sure you have what it is you're drawing and what the units are so we know what the scale is. So let's look at this. A point load, when we're looking at shear, a point load is going to change our shear diagram up or down. It causes a discontinuity in the direction of the load. So we are going to go up. Okay, we're going up, and we're going up to 73.75. Now what I like to do is just keep that in my calculator and kind of run through as we're going through. So now as I go from A to B, I don't have any change in shear. Okay, so it's going to be constant. B to C, I don't have any change in shear. Again, it's going to be constant. And then at C, I have another point load. That provides a discontinuity. It's going down, so my shear diagram is going to follow the same suit. So I have a negative 45. So I come down to 28.75 kilonewtons. Okay, it just came straight down. Now again, from C to D, I don't have any change. And the way you would look at this is if I cut it here, or cut it here, or cut it here, or cut it here, cut it here, cut it here, cut it here, wherever I cut it in there and I sum forces in the y direction, I'm not having any changes besides these two loads that are on there. So it doesn't matter where I cut it, it's going to be a constant 28.75. Okay, so now I have to come back and I have this nice uniform load. It is constant, which means it is a 0 degree load. And I know as I'm integrating my loads to get to my shear, if I have a 0 degree, we have to then be coming to a 1st degree. Again, my load is going down, so my shear is going to follow suit, and we already found that the area was 90 kilonewtons. So I have 28.75 kilonewtons, and I'm going to subtract off 90. Okay, and so at the end of this at E, I'm going to come down here to negative 61.25 kilonewtons. I'm starting here, I'm coming here, I'm going from a 0 degree load, from a 0 degree curve, so I know that this is going to be a 1st degree curve, if you want to call it that. It's linear, it's a function of x. Okay, and as I go, I don't know why this is not coming into focus super quickly, and I can't find my super quick focus button. There we go. As I'm coming from E to F, I have no change, so we're coming straight across. At my roller, I can come up 61.25 and kind of close that at 0. So we came up, we came down, and then we came back up. So constant is a 0 degree, 0 degree, 1st order, 0 degree. I need to make sure I have every point marked on my shear diagram where I have a change. And I need to note that where shear equals 0, the slope of my moment goes flat. And so this is an important note to note. So how do I figure out where that is? Well, I'm going to take 0.75, okay, that's what I have, this value right here, divided by my 30, and I get 0.958. So this value is 0.958, which means, change signs, 3 plus, this distance right here is 2.042. So now we can find the areas. So once again, we go from shear to moment. We're just finding that area under the curve. That's all the integration is area under the curve. So we are going to draw our line for our 0. moment, kilonewton meters. Okay, so again, what am I drawing? I'm drawing a moment diagram. What are my units? Kilonewton meters. When I start here at A, I have a pin. So as a reaction, it doesn't carry a moment. I also don't have an applied moment at A, so I know I'm starting at 0. And looking at this, I'm coming back to a roller, which doesn't carry moment. And again, I don't have an applied moment, so we know we've got to end at 0. And this is how, if I don't end where my reaction is, I've either screwed up my reactions or I've screwed up my shear diagram. I need to end where I am. I'm going to have to end at a 0. If I don't, I know to go back and look. So we're literally finding the areas under our curves. And I have to note that I have a change here. That's where I'm going to have my moment. So we're going to have an area 1, an area 2, an area 3, an area 4, an area 5, and an area 6. Okay. I'm going to try to erase if I can find an eraser in this mess. I'm going to erase, and I don't know where any of my erasers are. So I won't be doing any erasing. I was going to erase this so we could, oh, there it is. We could have room to work. Okay. So now what I'm going to be doing is area 1. I know that area 1 is a positive shear. It's a positive, so I'm going to have a positive moment slope. So remember, where I have positive shear area, I'm going to have positive moment slope. Where I have negative shear area, I'm going to have negative moment slope. What does that mean? Negative slope, positive slope. It doesn't mean it's a positive moment or a negative moment. It just means we're moving up or we're moving down. So area 1 is a rectangle, base times height. Okay, my base is 2 meters. My height is 73.75. Okay, so again, I'm starting at 0. 73.75, enter 2 times, and I get 147.5. So I'm going to 50, 100, 150. So we're going to come right up here. 147.5. Okay, I'm starting at 0. This is a 0-degree curve. And so I'm going to have a 1-degree curve coming up to that point. 1 degree. You need to make sure you're always marking the degree of curve. And again, any point where you might have a change or where you might cross a 0. So we have a 1-degree curve to 147.5, and I'm going to leave that in my calculator. Now I have this applied moment. So an applied moment, just like a point load, causes a shift up or shift down. It's a discontinuity. How do I know which direction it is? Well, I'm coming across and I have this moment of 120 kilonewton meters. Okay. So if I look internally, I'm going to have to be going equal and opposite to balance out. Okay, equal and opposite. This is an internal negative moment. So remember, inside we have normal, shear, bending moment, positive. Positive moment, negative moment. So we're going to drop down. So I'm going to subtract 120, and I get down to 27.5. So if this is 50, we come down to about here. I'm going to come straight down. Look at that, coming straight down. Negative moment coming straight down. And I need to list that that's at 27.5 kilonewton meters. I have my units on here. Now I'm going to come back over and I'm going to just go ahead and note that we are still at a base of 2 and a height of 73.5. So this area is also 147.5. So let's go back, 147.5 plus, and I get 175. So we're coming up to here. And that does not look like it's even close to scale. 175. I also know 0 degree, 1 degree. Okay. Positive area. So this is also a rectangle, base times height. So I have 2. That's my base. And my height is 28.75 times. So I get an area of 57.5. And I'm going to add that to my 175, and I get 232.5. Okay, 232.5. 232.5. 0 degree, 1 degree. I've still got a little bit more positive, and I know that where I come to a shear is 0, I'm going to go from a positive slope to a negative slope, so it's going to be flat somewhere in here. Okay, what is the area of a triangle? It is 1/2 base times height, so I have 0.5 enter. That's my 1/2. My base is 0.958 times, and my height is 28.75 times. So I get 13.77. That's my area. Just going to add that to it, and I get 246.27. So this is going to start to curve, and then we'll be curving back down. So we are looking at a parabolic. Okay, we're now curving. Okay, now we've coming down here to negative shear, so that means our slope of our moment is going to start coming back down. It doesn't mean we have a negative moment. We're way up here in this positive range. It just means our slope is heading back down. So 0.5 enter, 2.042 times, and then my base or my height is 246.27 times. So I get 251. Okay, 251, and that is not working out so well. Let's try that again. 0.5 enter, 2.042 times. It's because I was taking the moment value and not taking my shear, 61.25 times. That makes more sense. Okay, minus. So we're going to come back down to 183, which is somewhere in here. And I can see it's a 2-degree curve. The way I decide which way does it go, like a rainbow, like a spoon, is if I take a sliver and I look at a differential element here and a differential element here. Lots of area, little area. Lots of area, big slope, little area, flatter slope. Okay, differential element of this triangle. Okay, zero area, lots of area. Flat slope, bigger slope. Okay, so that's how I follow. Bigger area underneath, bigger the slope. As we approach 0, we're approaching a flatter slope. So I'm at 183.775, and again, it's just a negative direction, doesn't mean negative moment. And I'm back to a rectangle. So I have 3 enter, and then I have 61.25 times. Okay, that is a negative area. So I make that negative, I add it, and I get essentially a 0. 0 degree, 1 degree. And there you have it. I have labeled all of my points, peaks and valleys, where I'm having changes in 2 degree, 2 degree to 1 degree. Everything is labeled.